3. But where we left off last class was he said, okay, if you have more than one type of beta carbon, here we have 3 different beta carbons in our substrate. Remember, the substrate is the molecule that possesses the leaving group, our alkyl halide. We have 2 different types of beta carbons in there, and we decided that if we were to abstract the proton in blue, we would end up with what we call the Zaitsev product, which is the more stable product. If we abstracted the proton in green, we would end up with the Hofmann product, which is less stable. Remember, we said the more substituents, the more R groups we have in our double bond, the more stable it is, right? Okay. Then we said, okay, well, can we get one of these products preferentially over the other? And we see that when we use sodium ethoxide, okay, which is an unhindered base, so unhindered, meaning it is not very big, okay, it's going to pluck off whichever proton it can to give you the more stable product, and thus the Zaitsev product is going to predominate. However, we saw that if we use a hindered base, like this big old bulky one here, hindered base, okay, like potassium T-butoxide, I've left the potassium out, but anyhow, if we use T-butoxide as our base, it's so bulky that it is going to go for the beta carbon in green. Why? Because it's only attached to one carbon, and thus it's easier to abstract that proton. And so even though the Hofmann product is less stable, it would predominate in that case. And so we looked at this table here, and again, this is just a summary of what I just said. If we use an unhindered base, like ethoxide, so again, unhindered, okay, in that case, the Zaitsev product will predominate. But if we use a hindered base, like potassium T-butoxide, we see that the Hofmann product predominates. And if we use an even more hindered base, okay, then we see that the Hofmann product predominates in an even greater amount. And so kind of the way I ended the lecture last class is I said, what's kind of cool is that you can go to the reagent shelf or cupboard, and you can choose a reagent, and based off of the reagent that you choose, you're going to predominantly form either the Hofmann or the Zaitsev product. Maybe today you want to make the Hofmann product. Maybe tomorrow you want to make the Zaitsev product. Whatever. But we know how to do that. And we said, on top of all this, organic chemists love reagents. Okay, they love a new reagent. If you want to get an organic chemist excited, tell them, oh, I got a new reagent for you. They'll be like, oh, hot diggity darn. All right. So there are other hindered bases that we can use. These are called non-nucleophilic bases. Why are they non-nucleophilic? They're too big to be nucleophiles, right? They're too big and bulky to go and attack an electrophilic center. And so we have diisopropylamine and triethylamine, and I told you amines are organic bases. Okay, and I'm going to throw 2 others in there that are on that handout I gave you this morning. If you look on maybe the back side of it, there's one in there called DBU, okay, DBU, and there's another one called DBN, okay? DBU is a diazobicycloundecane, and then the other one, DBN, is on that handout as well, okay? And maybe I'll show their structures later on. But these would also be under the umbrella of non-nucleophilic bases. They're good at abstracting protons, but they are not nucleophilic whatsoever. All right, so where we left off was with these 2 scenarios. You see there's a big similarity between these 2 compounds. They're both alkyl halides. They're both tertiary alkyl halides. The only difference is that one has a chlorine, right, and the other one has a bromine. But if we look at this product on the top, if I highlight this double bond here, when they did this E2 elimination reaction, is this the Zaitsev product or is this the Hofmann product? Can anybody tell me? It's the Zaitsev product, right, because it's the more substituted. So Zaitsev, all right. And to form the Zaitsev product, what would we want to use? A hindered base or an unhindered base? Unhindered base, right? So we would use something like, it's saying here hydroxide or tert-butoxide. We'll just say we would prefer hydroxide in this specific case. If you want to draw a mechanism, you could say, well, this is my alpha carbon. This is the beta carbon from which I am abstracting the proton. My base is going to pick up the proton. I'm going to form the double bond, and I'm going to lose my leaving group like this. Now, for the next case, it must be the tert-butoxide. This one must be the tert-butoxide. And if we draw a tert-butoxide ion, okay, like this, we have this is our alpha carbon. Sure, this is a beta carbon, but that's not where the product is being abstracted in this case. We're abstracting this proton here, or one of those protons. And again, If you had written it on this methyl group, it's the same thing. Okay, it's the exact same thing because we have free rotation around sigma bonds. And so our base is going to pick up our proton. We're going to form the double bond. Oops, that's not very good. We're going to form the double bond, and we're going to lose our leaving group like this. And in this case, this is the Hofmann product, okay? When we form the less substituted alkene. But again, what's controlling the formation of this less stable product is the fact that you use a hindered base like T-butoxide. And again, for this one here, you could also use the triethylamine would work, the DBU would work, the DBN would work, any of those hindered bases, the diisopropylamine, etc., etc. All right, let's move on. And let's talk about a scenario where we have, there's only one possible place that we can put the double bond, right? Okay, it wouldn't matter if you abstracted one of those two protons that are highlighted, or if you plucked off one of these or one of these. Would you agree with me that you're always going to have a double bond between carbons 2 and 3, right? It's always going to be 1, 2, 3, or 1, 2, 3. However, when we have two beta protons, as we have here, and I'll just leave those ones in for instructional purposes, you notice that we can get both the cis and the trans compound, right? Here we have the trans compound. This is the trans, right? And then here we have the cis, and we can draw on the two protons here. And we went over this last class. I asked you guys when I showed you that space filling model, remember that one with the big spheres on it? And I said, I don't even think I would need to show you this. If I just asked you, based on your intuition, which one is more stable? And I think everybody was just like in unison. Everybody said the trans would be more stable. Why? Because it's less sterically hindered. And so we see here that the formation of the trans product, okay, this being the major product, is not only the thermodynamic product, but it's also the kinetic product, right? Thermodynamics, because the trans is more stable than the cis, but kinetic, why would it be the kinetic product? It's because what is lower? Activation energy, exactly, right? Your activation energy is lower. Now it says here, use this energy diagram in the Hammond postulate to explain why the trans isomer is formed. Well, I would just say, again, the transition state here is lower in energy, and therefore the trans isomer is going to predominate. All right, here's where it gets way more interesting. This is when we get into what's called stereospecificity, okay? And stereospecificity is going to require, the way that I do it is I like to use Newman projections to solve these. If you read the textbook, and sometimes you guys will come to my office or ask me, and say, in the textbook he did it this way, right? There's more than one way to skin a cat. There's more than one way to solve a lot of these problems, okay? I teach what I think is the most, straightforward way of doing it, but you'll see the textbook does it a different way sometimes, okay? And so when it comes to a beta hydrogen that's on a stereocenter, look at this very carefully. Would you agree with me that this carbon here, if I highlight that alpha carbon, would you agree with me that that's a stereocenter? That carbon is attached to 4 different groups. I think it's abundantly clear. Okay, it's attached to 4 different groups. Now, if you look at this beta carbon here, okay, you think, okay, if I'm going to do an elimination on this, my beta carbon needs to have a hydrogen on it. No tricks. Is there a hydrogen on this beta carbon that I highlighted in green? There's no hydrogen, so we can forget that one, okay? However, if we look at this beta carbon, sure, we see there's a nice hydrogen atom on there. Well, let me ask you another question. That beta carbon that I have highlighted in green now, is that a stereocenter? And again, it's not a trick. Is it? Is it attached to 4 different groups? Sure, yeah. So there's 2 stereocenters, okay? If the alpha carbon and the beta carbon are both stereocenters, in that case, the reaction isn't going to be selective. It's going to be specific, stereospecific. So if you're thinking, well, when it was selective, I could form the cis or the trans. If we go back here, okay, this reaction is selective, right? Selective for this product, right? The trans is going to predominate, but you're still going to get some cis. In this case, when you treat it, it is specific for, and you can see there's a big red X over the other one, it's not even formed. You only form this product. Now, the only way you would know this is either by reading the textbook or coming to class, and so that's what we're going to cover over the next probably 5 minutes is why do we only get this one isomer and we don't get any of the other isomer, okay? Now, if you're very astute, which I know you all are, I'll kind of tell you the Sparks Notes version of it first, then I'll get into the nitty-gritty, okay? The idea is this. When you eliminate the bromine and the hydrogen, right? Would you agree with me that in an E2 reaction, we're going to lose this hydrogen, we're going to strip it off, the leaving group is going to leave, and we're going to form a pi bond here. It's that the hydrogen and the bromine have to be in the same plane, right? You notice that neither of them are on dashes or wedges. They're both on just plain lines. That means they're in the plane of the page or the screen, whatever, right? They're all in the same plane. In order for an elimination reaction to occur, it's like the stars have to align, all right? Mike, everything has to line up. They all have to be what we call a coplanar, okay? And I'm going to go over because there's actually two types of coplanarity that we can have, okay? And I'll show you with a Newman projection. And so what we're going to do in a few seconds is we're going to be looking at our molecules and we're going to draw some Newman projections, and that's going to enable us to determine which stereoisomer the reaction will be specific for, not selective for. So here we go. This is the whole dog and pony show, and I'm going to distill this to the simplest possible bits I can, okay? To rationalize stereospecificity for a reaction, consider the transition state. In the transition state, all of this, okay, has to be rotated into the same plane, which I told you is called coplanar, okay? And you can see the word is down here as well. In other words, the beta hydrogen and the leaving group have to be coplanar, right? They all have to be aligned, all in a straight line. Okay, cool. What does that mean? Well, it actually turns out there's two ways that you can have the proton and your leaving group all lined up. One way is to have them completely anti to each other. You guys remember anti, right? So these would be anti to each other, and you see how they're all in a straight line? I just took my highlighter. Now, there's a student who was asking me a little bit about eclipse conformations who's not here this morning. But anyhow, you see how in here, even though it's placed slightly askew so you can read it, but technically that bromine is right behind the hydrogen, right? So they're technically coplanar when they're syn here as well. However, when it comes to the elimination reaction occurring, it only happens when the hydrogen and the leaving group are anti-coplanar to each other. It actually doesn't happen when they're syn coplanar. Thus, you and I, if everything is not presented to us on a silver platter saying, here they are, they're all coplanar, what we'll have to do is draw a Newman projection and change the conformation so that the leaving group and the hydrogen are all coplanar, but they're anti-coplanar to each other. Then we'll be able to figure out what the product is from there, whether we get the E or the Z alkene. And so, since it says here, the staggered rotamer, okay, where the beta hydrogen and the leaving group are anti-coplanar, is much lower energy, okay? So staggered rotamer, this one is much lower energy. The eclipsed one doesn't even happen. So, again, you're always going to seek to draw it like this. So the proton and the leaving group are all in the same plane, and then you're going to say, well, if I think about my carbon in the front, I'll highlight it in blue, okay? What about this carbon here? Well, the methyl and the phenyl are both attached to that carbon. But what's on the same side of the double bond as my methyl group? Well, you can see it's the tert-butyl group, right? The tert-butyl group is on the same side of the double bond. And then on the other side, we have the phenyl and the hydrogen. The only way to get good at this, in my opinion, is to practice it. But you're like, you say that about everything. Yes, I do. Okay, yes, I do. I totally admit that, okay? And so you're going to have to practice it, but students always get good at it. We always ask one or two questions about stereospecificity to make sure you're able to manipulate a Newman projection. And on the final exam, they always put a question, at least one of these, I would say, probably one, okay, on the exam. So make sure you understand that. However, there's one more term I want to tell you, which is this whole idea of being coplanar. If something was technically coplanar, it would mean that this angle here would be exactly 180 degrees. Well, that's a dream, okay? And in reality, the angles are usually off by a little bit, somewhere between 175 and 179 degrees, not exactly 180. And so you can't call them coplanar technically. There's a term that we use for it, and this is actually the term I'm going to use moving forward. Instead of saying they're anti-coplanar, I'll say they're anti-periplanar, okay, which means it accounts for the slight deviations. It means it's not exactly 180. Maybe you're sitting there going, oh, come on, man, you guys are getting too specific with the language. Well, anyhow, it's the term that we use in organic chemistry. Now, again, if you're thinking about, okay, we're making alkenes. You told me that if we could have trans or cis, the trans is more stable. I get that. But what if I have 4 different groups? Then is the E isomer going to predominate because E's are usually, not always, but usually more stable? You can see the answer here is you can't really guess your way through it. And none of you guys have ever tried to do that. I grade your quizzes, I look at them. Nobody's ever like, I'll just guess, But you can't guess it. It can't be done. If you do, you have a 50-50 chance of getting it right. It's either E or Z. However, it says, although the E isomer is usually more stable, since the transition state has to be antiperiplanar, you can't predict. Oftentimes we end up with the Z isomer, okay? So it's not uncommon to get that one. All right, let's practice this one. Now, in the textbook, he does it a little bit differently in some of his examples. What he does is this, I'll show you quickly, is he says, okay, if I look at this first molecule here, you can see the hydrogen and the bromine are in the same plane. You would agree. They're antiperiplanar to each other, right? They're all lying in the same plane. Well, he says, okay, well then just look at the R groups. You see that the red R groups are on the same side, right? They're both on wedges. And then you see that the blue ones are on the same side. So he's just kind of like, okay, just draw it like that. He says, make a double bond and say, okay, the 2 red R groups are on the same side. And then the 2 blue R groups are on the same side. And he's like, there you go, you're done, okay? However, what if the bromine is not, set up so that it's coplanar? Then you have to rotate it, Without drawing a Newman projection, I would just say, I've taught this class a long time, and I think it's trickier for students to rotate bonds without drawing a Newman projection. If you're good at it and you're confident in your skills, by all means proceed, okay? But sometimes people are like, I'm not sure, I think I need to draw a Newman projection first, and so that's what I like to do. If you're like, what do you mean by draw a Newman projection? I'll show you. If I asked you guys, we did this a few chapters ago. If I said, draw a Newman projection of this, what you would have drawn is this. Let me get my black pen. Okay, so we've got our carbon in the front, and we've got our carbon in the back. On the carbon in the front, we've got a hydrogen here. In the back, we've got a bromine going up like this. If we look at our R groups, right, the red R group on the carbon in front is over here. The blue one is over here like this. Then we have R1 over here, and we have R2 over here like this. So now we see that everything is perfectly antiperiplanar, or coplanar, whatever you want to call it. Anyhow, antiperiplanar, and so we can see that the R2 and R1 here are on the same side of the double bond. And so in this case, we're ending up with what looks like an E compound. Since they're different colors, I'll just call it an E compound. And so when we draw the double bond, we're going to say, okay, this time I've got, if I draw that double bond, I'm going to put my R2 here. And so this R2 is going to be, R2 would be here, and this R1 over here, and this R1 over here. I'll say it one more time. If you're sitting there going, you didn't have to do any of that, Mr. Dion, you're wasting time, okay? I noticed, maybe you're a student and you say, I noticed that these two were on the same side, and I noticed that these two are both on dashes. They're on the same side. Well, of course it's the E alkene. Don't waste your time with the Newman projection. Well, again, the Newman projection, as you'll see, will be handier when we have something where it isn't set up for us, where everything is perfectly coplanar, like in these examples. Okay, so let's take a look here. We've already gone over this. And this is just me. I guess I put this in here. I don't know why I did this. But anyhow, because I already mentioned it. Okay, so this is a rehash of a slide I did like 6 slides ago. Okay, I just think that maybe I didn't understand the term stereospecific or stereoselective, or maybe it was just mentioned quickly in my class. But again, stereoselective means you're going to have major and minor. Specific means you get what? One single product, okay? This is the way David Klein says it. He says if it's selective, you have a single substrate, but you get a major and a minor product. And he says if it's specific, well, you start with one thing and you get one thing in the end, right? You get one product. Go ahead.
So the idea behind this need to be in the same plane, that has to do with the pi orbitals needing.
Yeah, with the orbital overlap. Yeah, exactly. Otherwise, the elimination can't happen. You're getting into some deeper topics there, Eric, for sure. But yes, that's why. So for this class, Eric, we just say it's the requirement. Yeah, it's the requirement. All right, everybody good on the words selective versus specific? All right, rock and roll. Let's keep going. All right, let's give this one a try. Now, I'll try to distill it down into the simplest possible bits, but let's start with the first one, and we'll label the alpha carbon like this. Now, would you agree with me? There's two different types of beta carbons here. There's this one, I'll call this one the blue one, and I'll call this one the green one. Let me ask you guys, which beta carbon are we going to abstract a proton from with our base if we're doing an E2 reaction here? Which one? Would it be, are we going to take a proton off of the green carbon, the green beta carbon, or the blue beta carbon? The green, right? Are there any hydrogens on the blue beta carbon? No, it was kind of a, I always say there's no trick questions. It was borderline a trick question. You're like, there's no hydrogens on there, Mr. Dion. You're nuts, okay? You can just erase that. How many protons are on the green beta carbon? Right? Would you agree with me? There's two, okay? So in this case, right, remember, I said it's stereospecific when there's two chiral centers. A chiral center at alpha and beta. Is that a chiral center? No, there's two hydrogens on it. Therefore, don't have to draw a Newman projection, don't have to worry about drawing transitions or anything like that. All you have to do is say, I'm going to get cis and I'm going to get trans, or E and Z. So I'm just going to draw both of the protons in here, and we're going to say we're going to get a mixture of E and Z. So I want you to draw the E and Z products. Okay, so this is going to be, and I'll write down some additional stuff here. So stereo selective. Everybody wrote those down. We get a trans product in this case, and we get a cis product. Which one did we agree would probably be the major product in this case? The trans. It's going to be more stable. Yeah, thanks. Yeah, so we'll just say here trans, and we'll put here major. Okay, let's try the next one. The next one is a little more interesting, okay? So we're going to tackle this bad boy here. Okay, if we take a look at this. Now, this is our alpha carbon, this is a beta carbon. Are there any hydrogens on this beta carbon, right? No. On this beta carbon, how many hydrogens are there? Only one. Therefore, the hydrogen and the leaving group have to be anti-periplanar. The way that this is written, are they anti-periplanar? No, they're on the same side, right? So again, in the textbook, what he does a lot of times is he'll rotate this bond so that the bromine would be on a wedge, because if the bromine was on a wedge and the hydrogen, the beta hydrogen is on a dash, that means they're anti-periplanar to each other, okay? However, what I like to do is, like I said, draw a Newman projection. So what I'd like you to try, okay, and don't be shy, give it the old college try here. We're going to try to draw a Newman projection of what we see between these two carbons. Give it a shot. I know some of you guys draw it faster than me, okay? So let's, I'll give it the old... Okay, anybody get something like that? Good, I see people nodding, saying like, yeah, that's what I got. Okay, so I highlighted the proton, or the beta proton, and the leaving group, the bromine. Are they anti-coplanar to each other? No, so what are we gonna do? It's just like Wheel of Fortune. Spin that wheel, right? We're gonna just rotate that bond. So what I'm gonna do, since, you know, I'm teaching and I'm just going to do it like this. I'm going to take this guy and I'm going to move it over here, right? And when I do, then the hydrogen's going to switch position and then the tert-butyl's going to switch position. So let's rotate that bond, roll up the rim to win. All right, let's give it the old, that's an oval, not a circle. Let's try this. Is that better? There we go. All right. So we didn't touch the phenyl. We didn't touch the, man, oh man, can't draw a straight line. There we go. There's our methyl. So now our bromine is over here. Hydrogen is over here. Now would you agree with me that they're anti-periplanar or anti-coplanar to each other? Cha? What you can do is this. I like to do this sometimes. I noticed students were doing this the first time I taught this class, is they were kind of drawing lines through it like this and saying, okay, I can see that the phenyl and the tert-butyl are on the same side of the double bond, right? And then the methyl and the proton are on the same side of the double bond. And so when we draw the product, and it might not all be in the same orientation, but I think you guys have figured that out by now. Orientation doesn't matter. As long as the structure's right, it's good, okay? So let's just start by putting a double bond like this. The carbon in front, normally I wouldn't do this, but I'll put a little blue C on it there. And so it's got a phenyl on it, and it's got a methyl on it. So we've got a phenyl and a methyl. And we notice that the tert-butyl is going to be on the same side as the phenyl. You with me on that? So we're going to draw a bond up here, and we'll put the tert-butyl over here like this. And then we've got our hydrogen like this. Did you guys notice, if you drew this product, did you notice this is a Z product? Right? This is the Z alkene, zusammen, together, right? The phenyl has a higher priority than the methyl, and the tert-butyl has a higher priority than the hydrogen. Anybody get something like that? Anybody in there? Okay, good. All right. Just making sure somebody got it. So what I'd like you to try to do is for Saturday morning's class, Monday, I would like you to try to solve this one, okay? I'm sure you can draw a conclusion from it already. But anyhow, there you go. Stereospecificity, to me, as your teacher, it's a big moment in the class. For me, it's like, that's a pretty major reaction to learn, okay, I have to manipulate this thing and there's only one product I can get. But what we're going to see moving forward is you guys are good at drawing. I know everybody's really in the mood for drawing a chair, right? So what we're going to see is if we have a chair and it has a leaving group on it, the only way you can do an E2 reaction is for the proton to be anti-periplanar, right? Because if you look down this bond, you would see this leaving group is straight up and this is straight down, right? So if you had a hydrogen here, you can't abstract that hydrogen. You can only pull off that one. Does this make sense? We're going to get there in just a second. But this is kind of where we're headed with all of this. And so if we take a look at dehydrohalogenation, this is kind of what I was just writing on the board here, the same requirement must be satisfied in order for an E2 reaction to occur. Now, if you're looking at this molecule here and saying, okay, if I look at this and I think about this in terms of my Newman projections, Mr. Dion, there's actually two hydrogens in this molecule that are anti-periplanar to the chlorine, right? You'd say, well, there's one here, right? Because this is alpha, this is beta, but you'd say, yeah, but there's one here too. This one is also beta. I could eliminate either one of those. Does that make sense? Right? You see that he's drawing the Newman projection here, and all he's doing is highlighting this and this, okay, and saying that, yes, those are anti-periplanar to each other, and so an E2 reaction can occur. However, if the leaving group is equatorial, okay, and I know the answer's on the screen, but you look at that Newman projection right there. Do you see any proton that's anti-periplanar to that chlorine? I sure don't. No, there isn't one, right? If you look down here, that's a carbon, right? That's a CH2 group. And so so listen to me very carefully. The only way an elimination reaction can occur, okay, is for the leaving group to be axial and the hydrogen, the beta proton, to be axial. But they have to be opposite. One has to be axial and up, and the other one has to be axial and down. It's the only way the requirement can be met. And something I want to show you in just a second here is if you're like, oh, darn it, the chair, oh, I don't feel like it, I'm not in the mood. Don't worry. I'm going to show you that you don't have to draw a chair in order to solve these problems. Do you guys remember that up alternates, up and axial, then up and equatorial, right? Right. So as long as we can remember that, we should be pretty good to go. It says, take a look at these two molecules here. One will not be able to undergo an E2 elimination. Why? It might be helpful to draw their chair. It could be helpful, but I'm going to say it's not necessary. Watch. If I think about this leaving group, we all agree chloride is a great leaving group, dandy. Now remember, I said that in order for a leaving group to leave on a ring, it has to be what? Equatorial axial? It must be? Okay, let's try it again. In order for a leaving group to leave, or a beta proton to be extracted on a ring, they must be axial. So that means if we want to pretend like this leaving group can leave, if we're imagining that scenario, that would mean this leaving group, the chlorine, has to be up and axial, okay? So if we imagine this as being up and axial, what can you guys tell me about this proton, which is on the neighboring carbon, right? This is an alpha carbon, this is a beta carbon. That proton is going down and what? Axial. Down and axial. Alpha carbon, leaving group is axial. Beta carbon, there's a proton there that's axial and it's down. The other one's up. Do we have a winner? Can we do an E2 reaction? Oh yeah, right, big time. So what we could do is I'm just going to draw a generic reaction here and say, look, if you take this and you treat it with a base, I'll just put here, I don't know, it doesn't matter what it is, okay? But if it's going to pull off that proton, form the double bond, and you're going to lose the leaving group. And sure, you can do a beautiful E2 reaction, and you would end up with this compound here. This is called cyclohexene. So you've got cyclohexane. If you put one double bond in it, it's got a name. It's called cyclohexene. Now, let's do the same scenario with the other one, okay? If I zoom in, and let's just do our imagination here, and if we say that this chlorine is up, and it must be what again? Axial. Well, we see that we have a beautiful alpha carbon here, got a nice beta carbon here, but you can see there's symmetry in the molecule, so the beta carbons are identical. I'll just delete that one there. Okay, now on the beta carbon, in this case, we've got a methyl group and a proton. I'll ask you guys, this proton is up in what? Equatorial. Womp womp. Can we do an elimination this time? Nope. Right? Somebody's going, no dice. Not happening, right? Not today. Why? Because the requirement isn't met. And so you're like, you know what? I think if I studied this long enough and I look at the, right? I can say up and axial, down and, no, it's not going to work, right? Up and axial, down and axial, boom, it's going to work, right? So you don't even have to draw the chair out, okay? So we could just say here, look, base, and we'll just say no reaction. Nothing's going to happen, okay? Right? A good organic chemist, meaning you, me, we should be able to go to the cupboard and somebody says, try to do an E2 reaction on this molecule, and you're like, what? What's that?
Are you teasing me?
Yeah, where did you go to school? You know, or like, oh, you know, you need to retake 3101 or something like, right? Anyhow, he said, I learned that, you know, halfway through chapter 7. All right, good. Now, when it comes to this whole idea of regiochemistry, so which beta proton, Zaitsev or Hoffman, stereochemistry, cis trans, easy. So regio would mean Zaitsev and Hoffman kind of stuff. Stereochemistry would be more E and Z, and if you want to write cis and trans, that too. There's a whole bunch of things that you and I have to take into account, right? This is why organic chemistry is I won't use the F word, but to me it's interesting, okay? I was going to say fun, okay? But anyhow, I know that's offensive to some people. But anyhow, this is why it's kind of interesting, right? Will the substrate react specifically, right? Is there two chiral centers, or is it just going to be stereoselective? Or are you going to get a mixture of cis and trans, or E and Z? Yeah, and so it says here, and then again, these are David Klein's slides. Of course, I switch them up, and I mess around with them and post different practice problems in there. But he even wrote this: the only way to master this material is to do lots of practice problems. If any of you have taken a lot of math classes, right, and I know all of you have taken plenty of math classes just to get through high school, right? You're like, I did enough math in there, right? You always have some teacher who's like, it's a rainy day, let's do more math, you know? Anyhow, one thing that I think is different, in my opinion, between a subject like math and organic chemistry is anybody can relate to this? I know I can. That in mathematics, sometimes I'd be a little bit lost, and then all of a sudden I'd say, oh, now I get it. Here we go. And then it was like smooth sailing for the next 10 minutes. But anyhow, in organic chemistry, I think that can happen, but not really in the same way. It's not really like, no, you know, there's probably moments like that, but it's more like keep going and keep trying it and keep trying it and trying it. And then eventually, right, it starts to crystallize in your mind and say, okay, now I kind of see the full vision here, right? Okay, so if we take a look at this example here, and I'm not a speed guy, but I want to see how fast we can solve this. It says menthol chloride, when menthol chloride is treated with a strong base, so that's this guy here, okay, one elimination product is observed. Yet when neomethyl chloride is treated with a strong base, we get two elimination products. All right, I'm going to start with the menthol chloride and see if we can figure out why we only get one product. Watch. Let's label our alpha carbon. Let's label our beta carbons. I'm going to use two different colors because these beta carbons are different from each other. Now, if we want to pretend like there's going to be an elimination reaction that could occur, and they told us there is at least one, or there's one that can happen, that would mean that this leaving group, which is down, has to be down in what? It always, the groups, whatever's participating in the E2 reaction has to be what every time? Axial. So that would mean this is down in axial. Well, let's draw, oops, why will it not work? Anyhow, let's draw a beta proton in here. If we call this a beta carbon, right? That proton is going to be down in what? Remember, it goes down in axial, down and equatorial. Exactly. So this is down and equatorial. So can I get an elimination reaction occurring between these two carbons? That's a hard no. But, and you know, you can see where I'm going with this, right? If I scribble in this proton that's pointing up, this one must be up in what? Axial. Hot diggity darn. Can we get an elimination reaction occurring here? Yes, because we have an alpha leaving group that's axial. We have a beta proton that's axial. One's up, one's down. Let's go for it. All right, let's give it the old college try. So we're going to hit it with our base. I'll just put here generic base. Could be hydroxide, doesn't matter. Anyhow, so we're going to take our base. We're going to react. We're going to lose the leaving group. And let's draw our product. So we didn't touch that stereo center on the top. So we'll draw the wedge on that. There's an isopropyl group. We've got a nice double bond here. And we have our methyl. Sorry, my writing's a little shaky. But anyhow, are you with me on that one? Cool? All right, you guys ready? Let's try the other one. Okay, if we want to say, and they're telling us the answer. They're telling us that you can make two products with this. But in order for that leaving group to leave, it would have to be what? Up and axial. Let's go a little faster. This beta proton must be what? Down and axial, right? And this beta proton is also what? Down and axial, right? Remember, axial equatorial, so up and axial, down and axial, right? On adjacent carbons. And so we're going to form a double bond here in one scenario, and we're going to form a double bond here in the other scenario. Holy heck, two different products. Let's draw them both. So if we abstract that proton on the bottom, I'll draw the product in green if we can see it. But anyhow, we have the double bond here. There's our isopropyl, and you're like, hey, that's the same product on the last one, okay? That's the product that we drew before. These are the same. However, we can also pull off that blue proton, and when we rip off that blue proton, son of a gun, we're going to end up with something that looks like this. Now, this is not a stereo center anymore, so we get rid of that wedge, right? That carbon is sp2 hybridized, and we still have our methyl group like that. There you go. So we could call this the Zaitsev product, and we could call this the Hoffman product. However, it doesn't say whether it's a bulky base or a non-bulky base. We're just trying to flesh out the idea. How do we get two different products in one of them, and how do we get one product in the other? Cha? Okay. It seems like maybe it's Friday, everybody's tired, or it's just like, get me to spring break or something like that. But let's go over this one more time. Okay, when we're talking about E2 reactions on a ring, I'll just be blunt. The only rings we look at are cyclohexanes. Okay, the leaving group must be what? Axial or equatorial? It must be axial, and the beta proton must also be? Okay, good. All right, so we're good on that. So if you're like, well, how did you know the chlorine was axial or equatorial? I didn't, right? There's two conformations. There's one where it's axial, there's one where it's equatorial. I'm just going to say, well, in order for this to happen, it has to be axial. So I'll start with that, right? This is my starting point every single time, okay? There's a lot of questions that I put on here, and so I might just skip these for now and say, you know, you have the solutions to all of these, but I do want to show you one quick thing here. Because we've done a lot of work on these SN2 and E2 reactions. And this handout that I gave you this morning, again, if you don't have one, you can come grab one. And again, there's nothing magic in it. It's just a slide from the slide deck that I have posted to Canvas that I just photocopied for everybody. So you have it for reference when you're studying tonight or over the weekend or something. Okay? And what the heck was I talking about? Oh yeah, SN2 versus E2. But I think by now, you guys can all recognize a good leaving group, right? You got your iodide, your bromide, your chloride, your water, your tosylate. We said those are good leaving groups. But then we said, okay, well, what about substrates? What kind of substrates react best in an SN2 reaction? Would it be a primary or a tertiary substrate? For an SN2, it's a primary, right? And the opposite is true for an E2, right? So this is why organic chemistry is such a great litmus test for people who, are interested in things like medical school, right? You got to be able to make a judgment call, look at this, evaluate all the information and say, this is actually what is happening here, right? I have to decide what's happening. And so if we take a look at these substrates, they didn't put hydrogens on any of them, and so this must be a tertiary substrate. This is the same substrate here. Now, if I treat that with hydroxide, again, try not to be confused. Hydroxide, if you're like, hydroxide's a base, you're right, but it's also a nucleophile. And so you look at the substrate and you say, how is my hydroxide going to behave in the presence of this electrophile? Will it behave like a base, or will it behave like a nucleophile? And you say, well, the substrate is tertiary. It's not going to be an SN2 reaction, right? Because that works best with a methyl or a primary alkyl halide. Therefore, it must be an E2 reaction, right? This is the kind of decision tree we have to put together in our brain. And so if we just take a look at a couple of these, okay? And you might want to use this, okay? Because I don't expect you to remember everything the first day. That's not possible. But all it's asking in this specific case is it says, give us the major product for each of these. So I'll ask you guys, with the first one, okay, with this guy right here, what kind of substrate is that? Is it primary, secondary, tertiary, methyl? It is tertiary, okay, if you're not sure, right? This carbon is attached to 1, 2, 3 carbons. That is a tertiary, a beautiful tertiary substrate. Then I'd go over to my reagent, and I'd say hydroxide. Hydroxide is a strong nucleophile, but it's also a strong base. Now, in the presence of a tertiary alkyl halide, is it going to behave as a nucleophile or a base? A base, right? It's not going to be a nucleophile on a tertiary substrate. Then, and we're not done, how many types of beta protons are on this substrate? How many different types are there? Two. Right, Kevin? There's this type on the methylenes, and then there's this type here. If I pull off the blue proton, and I'll just draw it quickly, if you were to rip off that blue proton, you're going to end up with this product. However, if you ripped off the red proton, you would end up with this product. Now, is hydroxide an unhindered base or a hindered base? Unhindered. And so which product is going to predominate? We see the one in the blue is the Hoffman product, and the one in red is tri-substituted. It's the Zaitsev product. So which one would be the major product here? The Zaitsev product. And that's our decision tree. And there you go. We drew our major product, just like this. Okay? I'm going to give you a second to see if you can solve the next two. And if you're really fast, see if you can solve the next three. And again, use that decision tree that I gave you. You got methoxide, which can be a nucleophile or a base. You want to evaluate what kind of substrate you've got. And then we'll move on. Okay, did we have a primary, secondary, or tertiary alkyl halide in the first one? How many beta carbons is the alpha carbon attached to in the first example? No. The first example, meaning this one here. This is our alpha carbon, okay? How many beta carbons is it attached to? 1. Therefore, it is primary, okay? So then we come back here and we say, okay, we've got a primary alkyl halide. We've got methoxide as our base or nucleophile. And there's a line here that's hard to see in here and here. But anyhow, what this means is that SN2 will be major and E2 will be minor. And so we're going to draw the SN2 product as the major product. All right, so we go back here. And again, we've got a primary alkyl halide. And so SN2 will predominate. And so we'll draw the product of our SN2. What are the two steps of an SN2? You've got nucleophilic attack and loss of leaving group. And so we're going to have this, and then we're going to have OMe. And so you see that we made an ether here. Now, it's telling us to only identify the major product, so we'll just put here major. is the SN2 pathway. However, it is going to form some E2 product. How many beta protons are in this molecule? No tricks. 1, right? If this is, so look, I'll erase this. Here is our beta carbon, right? Alpha is, so let's go over it again. Alpha is the carbon attached to the halogen. Any carbon attached to alpha is a beta. There's only one beta carbon on here. You guys see it? How many hydrogens are on that beta carbon? 1. There's one measly proton on this guy, right? So if it was acting as a base and doing the E2, it's going to abstract this, form the pi bond, and you're going to lose the bromine as a bromide. And thus you would end up with this. We call this a exocyclic alkene. Okay? It's alkene leaving the ring like that. So that would be the minor product. So we'll put here minor, and this would be the E2. Okay? Let me give you a second to, again, go back to that handout. I'll be there in a sec and see if you can solve the next two. Okay, I'll give you a second to give that the old college try. Take a look at the next one. Okay, what kind of substrate do we have here? Is this a primary, secondary, or tertiary alkyl halide? Secondary. Okay, we get a nice alpha carbon here. But would you agree with me that there's 2 types of beta carbons in here? They're different, right? One has 3 hydrogens on it, this guy. And then this one here only has 1 hydrogen on it, okay? Now, if we go back to our decision tree, okay, we have a secondary alkyl halide, and we're treating it with methoxide, and so we see E2 is going to predominate. E2 will be the major product, but there's 2 beta protons, right? There's 2 different types of beta protons, like fiddlesticks. Okay, which one is it going to rip off preferentially? Anybody have an idea? Would it be the red one or the green one? So hold on, is this a hindered base or an unhindered base? No. Hindered has to be big. Methoxide is very small, right? Okay, methoxide, ethoxide, hydroxide, those are small. The only big one would be T-butoxide or DBU or DBN, something that's really giant, okay? And so if it's an unhindered base, which is going to predominate? Let's try it this way. The Zaitsev or the Hoffman? Unhindered base. Remember, this thing is small. It's like a ninja. It's like, I can go here, and I can go there. I'll do whatever I want. I can fit in anywhere I want. I'm going to make the most stable product because it's my choice, okay? Which, if it strips off the proton on the red carbon or the green carbon, is going to give me the more stable product? Red, exactly. So it's going to pull that one off, all right? There you go. So this is going to be your major product. So major, and we'll just put here E2, but Nicole had written down, right, we're going to get some SN2 as well. SN2 is going to be a minor product. But what happens when we do an SN2 on a stereocenter? We get what? Starts with inversion of, starts with C, ends with unfiguration. Anybody? Configuration, right? So we flip our dash to a, beautiful, right? There you go. Great, you guys, great. This is great. So we'll just say here SN2 minor. Now do you see why I printed this out before class this morning? That chart, right? You got to familiarize yourself with that, okay? Cha? All right, okay, let's keep going. Now in the next one, I'll even draw T-butoxide just to show you. You know, T-butoxide is a big old bulky base, right? We agreed. Now T-butoxide, you notice, isn't even on here. Okay, T-butoxide isn't on here, but it is an alkoxide base, right? And we have a secondary alkyl halide, but this thing is so big and bulky, right? It's never going to be a nucleophile. So if we have T-butoxide, it's never going to do an SN2, so we can just scratch this part off and say it's going to only be E2. But I'll ask you guys, if I draw this proton in red, that beta proton, and I draw this one in green, which one of those is it going to pluck off preferentially? Or is the only one it's going to pluck off virtually? Is the green one, right? Because it's less sterically hindered. Therefore, it's going to make the Hoffman product as the major product. And so we'll draw major product here in green. There you go. So this is our major, and this is E2. And there's going to be no SN2. let's make a note of that, okay? We'll say here, T-butoxide will never do SN2, okay? It can't happen. It's too big, okay? Actually, no, it's not true. It could do it on a primary substrate. You could get an SN2 in that case, but we'll never do SN2. I'll fix it. On secondary substrate, okay? Substrate. Beautiful. There we go. What time is it? It's 8:56 sugar. Okay, let me blast through the section on SN1 and E1. You notice that I spent all this time on SN2. I spent quite a bit of time on E2 with you as well. We did do stereospecificity, stereoselectivity, and all this. Yeah, but you notice you're like, SN1 and E1 are just chucked into the same section. Like, here you go, okay? Reason why is, you'll see as we go along here. So if we take a look at this reaction that's occurring here. Look, let's just take a break. We'll just go over this very slow. What kind of substrate is that? Primary, secondary, or tertiary? It's a tertiary substrate, right? It says it right on there, okay? So this is a tertiary substrate. Is this ever going to undergo an SN2 reaction? No. So there's no SN2. And you're like, well, come on. You put it in ethanol? What kind of a reagent is that? That's not a strong nucleophile. That's not a strong base, okay? But you notice it is on the handout. What do they call it on the handout? A weak base and a weak, there you go. So yeah, it can act like a base. And you're like, yeah, I've seen water act as a base. Sure, I studied enough chemistry to know that. Yeah, I've seen an alcohol act like a base in certain situations. But you notice here we end up with a mixture of products. And you're like, what kind of reaction is this? You're literally just dissolving the substrate in ethanol and you're getting products? Yep, that's the reaction. So it's not as elaborate, okay? Anyhow, we've gone over this. The first bullet point here, I covered this with you already. But if we go to the second bullet point, it says, it turns out the formation of the substitution and elimination products, okay, follows first order kinetics, which confirms neither SN2 or E2 is occurring. The reaction, the rate law for a first order reaction is going to look like this. Rate is equal to the rate constant multiplied by the concentration of the substrate only, and you can right there forget about the solvent if you want to. Okay, solvent is not going to affect anything, whether it's concentrated or dilute. It's going to react at the same rate. I guess the concentration of the substrate, but not the concentration of your ethanol is not going to matter in there. Anyhow, now what is going on in this reaction then? Well, remember I said it's SN together, E together. Well, SN1 is SN one at a time. We're still getting a loss of leaving group and a nucleophilic attack in an SN1 reaction. They just happen individually, right? It's a stepwise process. And in an E1, it's the same thing. First you get a loss of leaving group, then you get a proton transfer in the end. And so the first step of either of these, whether it's an SN1 reaction or an E1 reaction, the first step is the same for both of them. It's the loss of leaving group. Okay, so we lose a leaving group, and they're like, why would that happen? You answer. Why would that happen? What kind of carbocation is this? Is it primary, secondary, or tertiary? That's why it can happen. It's because tertiary carbocations are quite stable, right? After the carbocation is formed, there's two possibilities. Well, you get a positive charge plunked right there. You can either rip off a proton and make a pi bond and stabilize it that way to do your E1 reaction, or a nucleophile can just walk in and be like, hello there, positive charge, like let's make a bond and I'll do a substitution reaction, okay? It depends on, the solvent. So here's the mechanism of the SN1. First, we have our loss of leaving group, right? We form a nice carbocation. The nucleophile comes in, but you notice that since ethanol is a weak nucleophile, when it comes in, it's not done right away, is it? You notice that you end up with this species here, which we call an oxonium ion. And so you need to do one kind of extra step here at the end, which is a deprotonation, just a proton transfer. So we've got our loss of leaving group, our nucleophilic attack, but in this case, you need a proton transfer in the end to stabilize the product or to remove that positive charge. Sometimes we call these reactions solvolysis, because literally what's doing the reaction? The solvent. That's it. You just throw it in a solvent and a reaction happens, and the answer is yes. The problem with SN1 reactions is that it's a nice idea, and I like SN1 too, but if you throw it in ethanol, if you throw this tert butyl bromide in ethanol, you don't just get the SN1. Okay, you can't, if you're like, can I predict, or can I get one to predominate over the other? I'd say no, right? It's just going to be based off of the substrate. Now, something that I skipped over the first semester I ever taught this class here at UCCS 10 years ago, never forgot it, okay, is that I didn't hammer it home hard enough, I don't think, because a bunch of people missed this on the final exam, is what is the rate determining step? Do you guys remember rate determining steps from general chemistry? Okay, sometimes we call this the RDS, the rate determining step. It's the highest energy step in a whole mechanism, so a series of steps. It's the one that has the biggest activation energy. You can clearly see that this step has the highest activation energy. And so I want you to remember that RDS for SN1 or E1 is the loss of leaving group, which is the first step. Okay, it's always the first step that's the rate determining step. You can see that once that leaving group is lost, the rest is all kind of downhill from there, has much lower activation energies, all right? Now, this is just yammering on about stuff that I feel like I've covered in a lot of detail. I said the S in 1, S is for substitution, N is for nucleophilic, 1 was for first order. Gone over that quite a bit. And here's your generic reaction, and again, one thing I like about organic chemistry is we try to provide a logical answer for everything. Why does this happen? Well, the reason SN1 happens because you form a stable carbocation intermediate. The reason SN1 reactions don't happen with primary substrates is because primary carbocations are unstable. End of story, right? That's it. All right. Now, for the E1 reaction, I'm sure you could have figured this out without my help, but the first step is just going to be the loss of the leaving group, as I said. And the second step is just going to be pick off a beta proton, okay? Pick off a beta proton, but in this case, it's with your solvent. But remember, the solvent is a weak base, right? It's not a strong base, but it's a weak base. It can pull off a proton. And again, this is going to follow the exact same kinetics, where the rate is going to be equal to K multiplied by the concentration of your substrate only. Okay, just your substrate. And remember, the substrate is the molecule that possesses the leaving group. Okay, now some of the finer points are this: because SN1 and E1 reactions proceed through carbocation intermediates. What do you guys know about carbocations from the last chapter? I asked you a question about this on the quiz. Remember that I gave you 4 different scenarios and I said, can these rearrange? Yeah? Do you remember in section 6.12, the section we talked about reversible and irreversible arrows? Remember that? Do you remember what we said about a rearrangement? The arrow was always what? Irreversible. It was always just going in one direction. And so another way to put it, like a more politically incorrect way to put it, is just to say if carbocation rearrangements can happen, they do. Wipe your hands and walk away. And so if you're like, in SN1 and E1, I'm always making a carbocation. So do I have to ask myself, can this rearrange? The answer is yes. Yes. And thus, if this is a solvolysis reaction, right? When the leaving group leaves, okay, and you guys don't have to write this down if you don't want to, but I will, okay? We end up with this secondary carbocation. Based off of what you learned last chapter, this particular one that I have drawn in red, would it undergo a carbocation rearrangement? I see everybody nodding, right? You're ahead of me. Okay, you're like, yep, there's a hydride here. It's going to do a hydride shift. And you're actually going to end up with this, Mr. Dion. That's going to be the more stable carbocation. Well, you can see the nucleophile can attack either of them, can it, right? If it attacks the first one, you get this. If it attacks the second one, you get this. You're like, mixtures? Yep, mixtures is what we're going to get. Same thing with, and so that's just one scenario here, I should say. This one here is thrown on here too, which is just in SN1, in first order reactions like these on a tertiary substrate, I'd say a mixture is unavoidable. We end up with Hoffman products, Zaitsev products, substitution products. And if you look at that handout that I gave you, you'll notice that for all the SN1 stuff, it just has a line in the middle, and it doesn't even tell you which one predominates. Go ahead.
So the top one is going to rearrange, but the nucleophile might get to it before it
Yes. Yeah. So you end up with a mixture. Which is unavoidable. Now, going back to this whole idea here, if you were to ask me which one of these is going to be the major product, I'd say it would probably be a toss-up between these two. Maybe this one would be the major product. I think the textbook goes into more detail on this. I think what he says is this, is that if you have a tri-substituted alkene or a tetra-substituted alkene, those predominate, then the substitution product, then secondary, then primary, di-substituted and mono-substituted alkene, excuse me, okay? I'm not going to bug you about the specific order they come out in, but I do want you to be able to predict all of the products you could get of a solvolysis reaction, okay? All the different things that can happen in there. Now again, another slide that you guys know all this about these answers anyway. If you have a leaving group, by now I think everybody knows this in their sleep, right? Iodide is the best leaving group, then it goes down to bromide, chloride, and fluoride. And our rate determining step, again, for the SN1 and the E1, is the formation of the carbocation, which again, your rate determining step is going to be your loss of leaving group. And so the more stable the halide ion, the faster the ionization. If you want to take a break here for just a sec, if you've ever wondered, I remember being a student, I don't know if I wondered this or not, but if you're thinking, well, if iodide is the best, why don't we just use iodide for everything? Like, why would you even bother making bromides and your crappy chlorides and stuff? It's a great question. It's usually based off of cost, no joke. Okay, it's usually based off of cost. The most expensive one is an alkyl iodide, okay, very expensive. So we usually use those for small, little tiny experiments, in a lab. Then you go to bromide, which is somewhere in the middle of the road, good reactivity, decent price, right? Then you go to the chloride, which has the worst reactivity in a substitution and elimination, but they're a lot cheaper to make. Thus, whenever people are trying to do a reaction in an organic chemistry lab on a large scale, an example would be making a drug, okay? They'll usually do everything in their power to develop the chemistry so that it works with a chloride, because they can save so much money in the long run, right? But if you're just in the lab messing around and trying new stuff and you're like, I'm only using 10 milligrams of starting material, you might as well go bust out the iodide, we can afford this, let's just do this, see if it works, and then you kind of go on from there. Anyhow, so that's a little bit about why we don't always use the best leaving groups. Okay, this one here is a solvolysis reaction. And it says here, for the following solvolysis reaction, draw the substitution products and provide a mechanism for their formation. Now, in this one, we're starting out with a secondary alkyl halide. However, I would point out that they're telling you that it's a solvolysis reaction, and you are expected to know that if somebody says solvolysis and substitution, this means it's an SN1 reaction. Okay, let me ask you guys, what is the first step of an SN1 reaction? Loss of leaving group. I want everybody to draw the mechanism for the loss of leaving group, draw the product, and then see if it's going to undergo any rearrangement, yes or no. You guys see if you can figure that much out, which I know you can. Okay, on Friday the 13th. All right, so we will draw a loss of leaving group. Then I saw you guys had drawn, I'll just maybe draw the mechanism going down like this, okay? So we have our loss of leaving group. Then we end up with this secondary carbocation, right? But you guys, a bunch of people told me, they're like, yeah, that can rearrange. And then, remember, we have an irreversible arrow for a rearrangement. Then we're going to end up with this. So we have two different carbocations. Can the nucleophile come in and attack both of those? Yes, the answer is yes. I'm just going to draw the nucleophilic attack, draw the whole mechanism on the second one, okay? But we'll suss out the other one too. And so now what's going to happen here is that my water, I'm going to draw it like this. If you would draw the whole Lewis structure with the bent shape, by all means, go for it. Our nucleophile is going to come in. Maybe that's not going to work. There we go, like that. Okay, so we get our nucleophilic attack. But once that happens, we end up with this, where we've got a positive charge on our oxygen, like this. Are we done at this point? No. What's going to happen last? To make the alcohol, we have to do proton transfer, hot diggity darn. Now what's going to be our base in this case? I would say the water would be the base, okay? Every once in a while I'll have a student who says, well, wouldn't the bromide be a base? Yeah, it could be a base too, okay? I'll just draw the water. And anyhow, so we'll say our water's going to come along, okay? And it's going to pluck off this proton here, and there you go. You end up with that tertiary alcohol. And in the same way, this one, after the nucleophilic attack and the proton transfer, you're going to end up with this alcohol. All right, so we end up with a pair of alcohols in this case. It doesn't ask us to draw any elimination products. Go ahead.
I noticed they showed it with the stereo center first.
Yeah.
This guy's going to be like flat, right? So
Yeah, so exactly. So I'll ask you, right? This is sp3. That is a chiral center. What's the hybridization of a carbocation? It's sp2, right? So it's trigonal planar. It's flat. Therefore, when you look at this molecule here, I guess I should just highlight this carbon. That is a stereocenter. However, since it's planar, the nucleophile can attack indiscriminately from either side, and you would actually end up with a racemic mixture in this case. Okay, we have 1 minute left, so I will try to post the annotated slides, what I've got so far, since I'm going to assume many of you will be studying over the weekend for this. And make sure you do all the practice problems in the textbook, okay? Can't stress it enough. Just sit down, get a drink of Gatorade or something, no music. It'll just distract you, right? And then just start going through them. Cool? All right. If you have any questions,